The past couple of weeks we have discussed some of the Lanthanides, and in the poll you chose Yttrium, element number 39, that is also mentioned as a rare earth element. In fact, it was the first rare earth element ever to be discovered in Ytterby. Since all these elements are so similar, it raises the question, can Yttrium be considered the parent of all the Lanthanides or rare earth elements? Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell if you never want to miss another episode. Also, if you want to influence next week's experiment or element, make sure to fill in the poll in the comment section of our channel. Now look at this beautiful silvery gray metal. This is really something, right? Who am I kidding? When we compare this metal to erbium, lanthanum and scandium, we understand why scientists had so many issues separating them from each other. In its pure metallic form, they all seem to have the same shine, the same color. So it's not strange that they form this group. Now, after 3 episodes of rare earth elements, I do not think that anyone would still want to buy another one. But if you want a piece of Yttrium, make sure to click on the link in the description, and if you use the code, you will get a 10% discount and you will also be helping out our channel. Now let's start our journey again at a familiar place in the late 18th century, in a quiet Swedish village named, yes, Ytterby. Picture a small, out-of-the-way town with a humble quarry, the kind of place where nothing much usually happens. In 1787, an army lieutenant named Carl Axel Arrhenius, who was an amateur chemist in his spare time, was exploring that local quarry. Amid the ordinary stones, he stumbled upon a strange, heavy black rock that didn't match anything known. This mysterious rock was unusually dense and piqued Arrhenius' curiosity. Hoping he'd found something new, he named the rock Ytterbite, after the village Ytterby, and sent samples off to expert chemists for analysis. One of those samples landed on the workbench of Johan Gadolin, a Finnish chemist working at the Royal Academy of Turku. Gadolin received the black rock and got to work analyzing it in 1789. What he found was astonishing. About 38% of the rock was made of a substance that didn't correspond with any known element. In an era when scientists were just beginning to categorize the elements, this was like finding a secret ingredient in a recipe everybody thought they knew. Gadolin had discovered a new oxide, or earth as they called metal oxide back then, hidden in the mineral. By 1794, he had fully analyzed the oxide and confirmed it was something entirely new. This was the first glimpse of what was now known as Yttrium, though at the time they only had an oxide form, which Gadolin dubbed Yttria. News of Gadolin's discovery quickly spread, and another chemist, Anders Gustav Eckeberg, soon stepped in to verify the findings. In 1797, Eckeberg confirmed the existence of this new oxide and gave it the name Yttria, directly honoring the mineral Ytterbite and indirectly Ytterby village. Back then, discovering a new earth was essentially equivalent to the discovery of a new element, even though they hadn't isolated the pure metal yet. So, by the turn of the 19th century, the element within Yttria had been recognized. Yttrium has entered the scientific world, at least on paper. Isolating the pure metal Yttrium, however, was a bigger challenge. It wasn't until 1828 that chemist Frederik Wöhler managed to extract yttrium in metallic form. He reacted yttrium chloride with potassium to finally obtain a sample of pure yttrium metal. Now imagine Wöhler peering through his apparatus and seeing packs of a shiny new metal. It must have been an exciting moment. At least yttrium was not just an obscure oxide, but a tangible silvery metal that researchers could hold and study. For a while, the element was even represented with the symbol YT, after Yttria, before scientists later shortened it to the single letter Y, which we still use today. Yttrium's discovery turned out to be just the opening act in a much larger story. The black rock from Ytterby was like a treasure chest of new elements. In 1843, Swedish chemist Carl Gustav Mosander, which we have discussed now for weeks, revisited Yttria and made a surprising revelation, that Yttria oxide was not just a single pure substance at all. Mosander found it was actually a mixture containing at least 3 different oxides. He managed to separate them by slightly differences in color, one remaining white, still the yttrium oxide, but the other one was yellow, and the third one was rosé colored. At the time, Mosander named the yellow one Erbia. Hey, we remember that one from a previous episode, and the rosé colored one Turbia. If you want to see this episode, make sure to watch the erbium episode. In the erbium episode, I also explain how those two names got mixed together and eventually we got terbium and erbium. Make sure to watch this episode. But the parade of discoveries didn't stop there. In 1878, the Swiss chemist, and here we go again with the strange names, Jean-Charles Galissard de Marignac, managed to tease out another oxide from the mix, which became ytterbium oxide, yielding the element ytterbium. Over the next few decades, chemists isolated even more new metals from that same original ytterbium source. In total, that single Swedish quarry, mysterious ore, gave birth to at least 7 new elements. 4 of them, yttrium, terbium, erbium, and ytterbium, were explicitly named in tribute to Ytterby village, making it the world's most celebrated hometown in the periodic table. Now, during those early years, yttrium itself didn't have much use outside of the laboratory. It was a scientific curiosity, if you want. Part of the quest to understand the new category of rare earth elements. In fact, Gadolin's discovery of yttria is what gave rise to the term rare earth. Earth, as in oxide, and rare because these substances were new and scarce in pure form. Now, for much of the 1800s, yttrium and its rare earth cousins were mainly studied by chemists trying to unlock their secrets. But that didn't mean yttrium would remain obscure forever. Its time to shine, sometimes literally, was yet to come. Now, like many of the other rare earth metals, it's a silvery, gray, lustrous metal, as you can see also in the cube. And it's a relatively, like the other ones, soft metal. Not quite as soft as lead, but you could probably cut it with a knife if you want to. Yttrium is also fairly light, lighter than its lanthanide cousins, and it crystallines in a hexagonal structure. One interesting thing is that yttrium is a highly crystalline and pure samples can show beautiful crystalline features. It's a solid metal at room temperature, with a melting point of around 1526 degrees Celsius or 2780 degrees Fahrenheit. So it can withstand quite a bit of heat before turning into a liquid. Chemically, yttrium behaves a lot like the lanthanide elements. In the periodic table, yttrium is found in group 3, right above its big brother, lanthanum, the first lanthanide. This position is a clue. Elements in the same column often share similarities. Now, yttrium almost always forms a +3 oxidation state, meaning it likes to give up 3 electrons and forms Y3+ ions, just like the lanthanides typically do. Because of this, yttrium's compounds and solutions act remarkably like those of lanthanides such as erbium or dysprosium. In fact, if you dissolve some yttrium in a solution alongside heavy lanthanide elements, it would be hard to tell them apart by chemistry alone. They all behave like trivalent metals that don't change oxidation states easily. Another important aspect is the atom size. Yttrium's atoms are about the same size as atoms as the heavier lanthanide atoms due to a phenomenon called lanthanide contraction. That's a fancy way of saying that the lanthanides shrink a bit as their atomic number increases. Because of the similar size, yttrium can fit into the same mineral crystal structures as those heavy lanthanides. It's one of the reasons why in nature yttrium always is found mixed with other lanthanide minerals. Their ions can swap places in the mineral's crystal lattice with ease. Yttrium is kind of like a close cousin to the lanthanides, tagging along wherever they go. In terms of reactivity, yttrium is not a drama queen metal like sodium or potassium. It won't explode in contact with water or anything exciting like that. In fact, a chunk of yttrium metal is fairly stable in air because it forms a thin protective layer of oxide on its surface, yttrium oxide, Y2O3. This transparent oxide layer pacifies the metal, preventing further corrosion, rather like how aluminum protects itself. So if you left a piece of yttrium on a shelf, it would stay shiny for a long time without rusting away quickly. However, if you grind yttrium into a fine powder, it will become a different story. Those tiny particles can ignite in air at high temperatures around 400 degrees Celsius or above. Fine yttrium metal can catch fire and burn with a brilliant spark, forming yttrium oxide smoke. So while solid yttrium is content to just sit and keep its cool, powered yttrium can literally get fired up when heated. Yttrium's single naturally occurring isotope, Y89, is stable. This means all the yttrium you find in nature is essentially one kind of atom, with 39 protons and 50 neutrons. It doesn't have multiple stable versions like some elements do. There are radioactive isotopes of yttrium made in labs or byproducts of nuclear reactors like Y90, but we'll get to why those are useful in a bit. Magnetically, pure yttrium metal is not magnetic. It's actually paramagnetic, which means it's weakly attracting in a magnetic field, but it doesn't hold magnetism itself. And unlike some of its other lanthanide pals, yttrium isn't known for its colorful ions or fluorescence on its own. But, as we will see when combined with certain other elements, yttrium becomes part of some very colorful applications. If yttrium were merely a chemical curiosity, we probably wouldn't be making a video about it. Just kidding. Of course we would be making a video about it because we're making a video about every single element in the periodic system. The truth is, yttrium has a pretty impressive resume of applications across various industries, even if it works mostly behind the scenes. Let's explore how this underappreciated element pops up in our lives and technology. One of Yttrium's star roles has been in making color televisions and LED displays possible. Back in the day of bulky cathode ray tube CRT televisions, getting a good red color on the screen was a challenge. Compounds like yttrium oxide or yttrium vanadide doped with a bit of europium became the red phosphor that gave TVs their rich reds. So, if you ever watch classic TV and admire the red hues, you were unknowingly watching yttrium at work, converting electron beams into bright red lights. Now, in modern times, similar yttrium-based phosphors are used in LED lights. For example, yttrium aluminum garnet, YAG crystals, doped with cerium, produce a yellow phosphor that helps turn blue LED light into a warm white glow. Now, without yttrium compounds acting as hosts for these glowing europium or cerium ions, our screens and LED bulbs might have looked a lot duller. It's fair to say that yttrium has helped bring color to the electronic world. Yttrium also plays a crucial role in high-tech lasers. A famous example is the ND-YAG laser, which stands for neodymium-doped yttrium aluminum garnet laser. YAG is a crystal where yttrium and aluminum form a sturdy lattice, and a bit of neodymium provides the laser action. These ND-YAG lasers are the workhorses in industry and medicine. They can cut through metal, etch precise patterns, and even remove tattoos or perform laser surgery. The yttrium in the YAG crystal is essential the structural support that holds the active laser ions in place and withstands high power. Other garnet crystals with yttrium, like yttrium iron garnet, YIG, have special magnetic and optical properties. YIG is used in telecommunications as a microwave filter and in some optical equipment. To top it off, YAG crystals can be used in synthetic gemstones. An yttrium aluminum garnet can be used to cut resembled a diamond for jewelry. So yttrium gets to be both laser hero and a fox diamond. Not many elements can claim that range. Perhaps one of the most life-saving uses of yttrium comes from the radioactive isotope Yttrium-90. Y90 is used in a form of cancer therapy. Doctors attach this radioactive yttrium isotope to special molecules, monoclonal antibodies or tiny beads, that seek out the cancer cells or tumors. Once delivered, Y90 emits a strong beta radiation that zaps the tumor from the inside. Now, one such treatment is called radioembolization for liver cancer, where yttrium-loaded microspheres are injected into the blood, feeding a tumor lodging there and destroying cancer cells with radiation. It's a targeted therapy that can shrink tumors with minimal surgery. Y90 is also used in treating lymphoma in a drug called Zephyrin, where it's bound to an antibody targeting cancerous B cells. Now, beyond cancer, tiny Yttrium-90 sources have been used as precision knives in surgery. For example, cutting nerves in the spine to relieve pain in cases where other treatment fail. The idea of an atomic scalpel is pretty sci-fi, but Yttrium made it real. Though the radioactive isotopes does the heavy lifting, it's a role only Yttrium can fill in these therapies. Importantly, the stable Yttrium-89 in our bodies, we all carry trace amounts, doesn't do anything biologically. Yttrium isn't used by any living organism naturally. It's there in tiny amounts from food or the environment, but it serves no biological function. So, we really harness yttrium's power mainly in technology and medicine, not in biology. Yttrium might not be a household name, but it's hiding in materials that improve our daily tools. A small dash of yttrium added to metals like aluminum or magnesium make those alloys stronger and more heat resistant. This is extremely valuable in aerospace and automotive applications, where you want lightweight metals that can handle high stress and temperature. For example, adding just a fraction of a percent of yttrium can help aluminum alloys resist high temperature oxidation. Imagine a jet engine part that runs red hot yttrium helps it not degrade in all that heat. Yttrium also helps to refine grain size in chromium and other metal coatings, improving their durability. In the world of ceramics and glass, yttrium oxide is used to make materials that can withstand thermal shock, such as a camera lens glass that doesn't crack under quick temperature changes. Some high-performance camera lenses and scientific instrument glasses incorporate yttrium for this reason. And if you've ever used a camping gas lantern, the kind with the glowing mantle, you might be interested to know that yttrium is used in the gas mantles as well. It replaced the older radioactive thorium mantles to produce a safe, bright light when heated. Yttrium oxide in the mantle emits a brilliant white light when incandescent, illuminating many campsites without the risk of radioactivity. From alloys to glass to old-school lanterns, yttrium quietly makes materials tougher and brighter. In 1987, yttrium made headlines around the world for a discovery that seemed like scientific magic. Researchers at IBM and universities found that a compound of yttrium, barium, and copper oxides, abbreviated YbCO, could become a high-temperature superconductor. This meant that below a certain critical temperature, about 93 Kelvin, which is minus 180 degrees Celsius, YbCO conducts electricity with zero resistance. Now, what was revolutionary is that 93 Kelvin is above the boiling point of liquid nitrogen, making it much easier and cheaper to cool than previous superconductors that needed ultra-cold liquid helium. Yttrium's name was suddenly in the news, attached to this exotic ceramic material that levitates magnets and promises lossless power lines and maglev trains. While we are still working on practical widespread superconductors, YbCO is used in some applications like MRI machines, particle accelerators, or experimental power cables. It's quite poetic that yttrium, the element discovered as part of a black mineral over 230 years ago, became the key to one of the most cutting-edge materials of the 20th century. It shows how even the quiet elements can surprise us in a big way. So let's tackle the big question. Can yttrium be considered the parent of all lanthanides? This is an interesting idea that comes from yttrium's unique relationship with the lanthanide series. First, some clarity. The lanthanides are the 15 elements with atomic numbers 57 through 71, starting with lanthanum, which we've discussed a couple of weeks ago, and ending with lutetium. Yttrium, with atomic number 39, is not one of them, so strictly speaking, yttrium is not even a lanthanide itself. Now, it actually sits one row above them in the periodic table. However, yttrium is often honorary family. Chemists include it as one of the rare earth elements, a group that bundles the lanthanides together with yttrium and sometimes scandium too. Now, why is that? Well, because yttrium is always found with the lanthanides in nature and behaves so similar to them chemically. It's like that friend who isn't a blood relative but shows up at every family reunion and fits right in. So, can we consider yttrium the parent of all lanthanides? In a historical and practical sense, yeah, we can. Yttrium's discovery led to the, so to speak, birth of the lanthanide series in chemistry, and it continues to be closely related and associated with them. It was the first rare earth found. It's present wherever lanthanides are, and scientists even named a group of those elements after yttrium. But in a strict scientific classification, no, yttrium is not itself a lanthanide. So it's more like an honorary family member rather than a literal parent. It's a semantic distinction, but an important one for chemistry geeks. So yttrium was one of the first rare elements to be discovered. Now if you can't get enough of the lanthanides, take a look at the video we've made about scandium, one of the elements that is often referred to as a rare earth element, but isn't a lanthanide itself. If you think I missed anything, put it in the comments, and if you like this video, like, subscribe and make sure to hit the notification bell so you will never miss another episode.